Welcome back. Today, we're really diving deep into something pretty fundamental for cloud-native computing. It's all about how Kubernetes handles, well, persistent data. Now, anyone who's tried running stateful apps in Kubernetes bumps into this paradox, right? Containers, they're meant to be temporary, ephemeral, spin them up, tear them down. But what about your database or user uploads, critical files, stuff that absolutely has to stick around? For a while, this was, a real headache. So today, we're pulling back the curtain on Kubernetes' solution: persistent volumes and persistent volume claims. Usually you hear them called PVs and PVCs. Our mission here is basically to cut through the complexity, give you a shortcut to understanding what these are, why they're so essential, and how they actually work to keep your data safe and available, even when your apps are scaling like crazy. Okay, let's start unpacking this. We hear PV and PVC thrown around all the time in the Kubernetes world. What exactly are they? What's the core problem they're designed to tackle?
Yeah, it's a great question because they really introduce this crucial separation of concerns. So a persistent volume, or PV.
Hmm.
Think of that as the actual concrete piece of storage. It's in the cluster. It could be, a chunk of network storage like NFS, or maybe an AWS EBS volume, or a Google persistent disk, something an admin has set up, or maybe something created automatically. It's the real storage resource.
Okay, the physical or virtual physical storage.
Right. Then you've got the persistent volume claim, the PVC. Now, this isn't the storage itself. It's more like a request for storage made by a user, or usually an application. It's like a pod's way of saying, hey, I need storage. It specifies things like how much size, maybe performance needs, how it needs to be accessed, like read-write for one pod, read-only for many. But the key thing is, the person writing the application config. They don't need to know the nitty-gritty details of where that storage actually comes from. The PVC is like the ticket, the claim check.
Okay, that abstraction idea is really hitting home. PD is the storage locker. PVC is the request slip saying, I need a 10 by 10 locker. Is that a fair way to think about it? Like a USB drive versus asking for a USB drive?
That's a really good analogy, yeah. The PV is like having a box of available USB drives, maybe different size, the different speeds already plugged into the cluster's hub. And the PVC, that's your application saying, I need a USB drive, about 5 GB, please. Kubernetes then finds a matching PV from the box and kind of reserves it for that request. Then your pod, your container, uses that PVC, that request slip, to connect directly to the specific PV, the actual drive. And boom, you can read and write data. And crucially, unlike, say, empty dir, which is temporary, this storage persists. It stays around even if the pod gets deleted or restarted.
So let's ground this. What are some common, everyday examples where you absolutely need this PV-PVC setup?
Oh, tons of places. The most obvious one is databases. Running MySQL or PostgreSQL or MongoDB, their data files have to live somewhere permanent. So you'd use a PVC. Or think about a file sharing app. People upload files, right?
Yeah.
Those files can't just vanish if the web server pod restarts. They need persistent storage, managed by a PV and requested by a PVC. Same goes for something like WordPress, a content management system. Your posts, your themes, your uploaded images, all that needs to persist. Basically, any application that holds state you care about.
That makes sense. It sounds fundamentally important. But let's push a bit further. Beyond just saving data, why are PVs and PVCs considered so critical? What are the bigger wins for someone managing a Kubernetes cluster?
Well, the core problem they solve, as we touched on, is that containers are ephemeral by design. Their internal file system, poof, gone when they restart and get moved. For any app that needs to remember things, PVs and PVCs provide that reliable, flexible way to attach persistent storage. It ensures your data survives, it's durable, and it can even move around the cluster with the application if needed.
Okay, durability. What else?
So a few key reasons jump out. First, as we said, data persistence. That's the big one. Data stays even if pods die, restart, or get rescheduled. Absolutely critical for stateful apps. Second, and this is huge, is the abstraction of storage. The PDC lets developers just ask for storage. I need 10 GB with read-write access without needing to know if it's backed by AWS EDS or Google PD or some on-prem NFS share.
Right. The developer doesn't need to be a storage expert.
Exactly. It massively simplifies things for them. They focus on the app, not the underlying infrastructure details.
That sounds great for developers, but what about the ops side? Does it help them too?
Absolutely. That brings us to dynamic provisioning. This is super powerful. Using something called storage classes, a PVC can actually trigger the automatic creation of a PV. So the admin defines types of storage available, like fast or cheap archive. When a developer requests storage via PVC, Kubernetes can automatically carve out a new PV of the right type. No manual ticket needed for every volume. It scales beautifully.
So it automates a lot of the grunt work for the infrastructure team.
Totally. And it also enables portability across environments because the PV-PVC model works with so many different storage backends, cloud disks, NFS, Ceph, Gluster FS, you name it. Your application definition stays largely the same whether you deploy on AWS, Azure, GCP, or even on-prem. Much easier to move apps around. And lastly, it helps with resource management. PVCs let users be specific about their needs. I need exactly 8 GB. This means you allocate storage more efficiently. You don't just give everyone a massive disk just in case. Prevents waste.
Okay, that paints a clear picture of the benefits, but what's the flip side? What happens if you, I don't know, try to cut corners? If you don't use PVs and PVCs for apps that need to save data, what kind of trouble are you asking for?
Oh, you're asking for a world of pain, honestly. We see this sometimes, especially with teams newer to Kubernetes. Maybe they try using host path volumes, tying storage directly to a specific node's file system.
What's wrong with that? Seems simple.
Well, it is simple until that node fails. If the node goes down, the data on its host path volume is likely inaccessible, maybe even lost depending on the failure. Your app is dead in the water, and recovery can be a nightmare.
Yeah.
Or they might just rely on MPDIR, which is fine for temporary scratch space, but any data in there vanishes the moment the pod stops. So if your database pod restarts, all your data is gone. Completely unsuitable for anything persistent.
Yikes.
Yeah. Without PVs and PVCs, you either risk data loss or you create fragile applications tightly coupled to specific machines. Scaling becomes incredibly difficult, reliability plummets, it makes running serious stateful applications almost impossible in a dynamic cluster environment.
Can you maybe illustrate that with that photo app example again? Show us how the PV-PVC setup prevents that kind of disaster.
Sure, let's take that photo sharing app. Users are uploading pictures constantly. That data must survive. So the deployment includes a PVC definition saying, I need 50 GB read-write once access. Kubernetes, maybe using a storage class linked to AWS EBS, dynamically provisions a 50 GB ADS volume, that's the PV, and binds the PVC to it. The application pod mounts this PVC at, say, uploads. Now, users upload photos. They get written to that EBS volume via the pod. Okay, now imagine the pod crashes. Or maybe the node it's on needs maintenance, and Kubernetes decides to reschedule the pod to a different node.
Right, the pod moves.
Exactly.
Wow.
But because the storage is this independent PV, the EBS volume, Kubernetes just detaches it from the old, now dead pod location and reattaches it to the new pod location on the new node using the same PVC.
Ah, so the pod moves, but the data storage effectively follows it.
Precisely. The new pod starts up, mounts the PVC it uploads, and all the photos are still there, safe and sound on the EBS volume.
That's the power of decoupling the storage lifecycle from the pod lifecycle. Okay, fantastic. We've got the what and the why pretty clear now. Let's get into the mechanics. How do PVs and PVCs actually work together under the hood? What's the dance between them to connect an app to its data?
It's a well-orchestrated process, really. At a high level, PVs represent available storage, PVCs represent requests for storage, and Kubernetes acts as the broker. It all happens declaratively, usually defined in YAML files that you apply to the cluster. An admin might set up some PVs manually or define storage classes to enable dynamic provisioning. Then developers create PVCs in their application specs. Pods then reference those PVCs to get access.
Okay, declarative sounds good. Less imperative scripting, more desired state. But walk us through the typical flow. Let's say I'm a developer, I need 5 GB for my database. What are the actual steps that happen in Kubernetes?
All right, step by step, it usually looks something like this. 1. Someone provisions the persistent volume, PV. This could be an admin manually creating a PV object that specifies, say, capacity, 20G, access modes, read-write once, and details about the actual storage backend, like an NFS server path or a cloud disk ID. Or, and this is more common now, there's a storage class defined. We'll talk more about that. But it allows PVs to be created automatically when needed.
Okay, so the storage resource exists or can be created, step 2.
2. The developer creates a persistent volume plane, PDC. This is usually part of their application's deployment files. The PVC YAML would say something like storage, 5G, and access modes, read-write once. Crucially, it might also specify a storage class name to request a type of storage, like fastST. Kubernetes control plane sees this new PVC. It then looks for an existing PV that matches the requirements, size, access mode, maybe labels. Or if a storage class was specified, it tells the storage class provisioner to create a new PV that matches.
So Kubernetes does the matching or triggers the creation, and then they're linked.
Exactly. The PVC gets bound to a specific PV. Think of it like assigning that USB drive from the box to fulfill the request slip. 3. The pod mounts the PVC. In the pods definition, like in a deployment or stateful set, under volumes, you reference the PVC by name. And then in the container spec, under volume mounts, you specify where inside the container that volume should appear, like varlet console.
So the pod just asks for the PVC name, and Kubernetes handles connecting it to the right PV and making it available inside the container.
Precisely. Kubernetes makes sure that underlying PV storage is mounted on the node where the pod is running, and then mounts it into the specified path within the container's file system. The application just reads and writes to that path. And 4, persistence and reattachment. This is the payoff. If that pod gets deleted or crashes or is rescheduled, the PV and the data on it remain. When a new pod starts up that references the same PVC, Kubernetes ensures it gets connected back to that same PV. So for our database example, if the pod restarts, it mounts the PVC at varlet console again and finds all its data files exactly as they were.
That lifecycle makes a lot of sense. You mentioned storage classes and also access modes and something called a reclaim policy. Can you elaborate a bit on those? They sound like important details for tuning this.
Definitely. They add a lot of the power and flexibility. So storage class. Think of this as defining different flavors or tiers of storage available in your cluster. An admin creates storage class objects. One might be called FastSD and use premium cloud disks. Another might be bulk HDD using cheaper, slower storage. Or backup NFS pointing to an NFS server. The storage class specifies which provisioner to use, like the AWS EBS provisioner, the NFS provisioner, etc., and any parameters needed, like disk type IO1 versus GB2 on AWS. When a PVC requests that storage class by name, the provisioner automatically creates a suitable PV. It's key for dynamic provisioning.
So it lets admins offer a menu of storage options, and developers pick from the menu via their PVC.
Exactly. Then there are access modes. These define how the volume can be mounted simultaneously. There are 3 main ones you'll see: read-write once, or RWO. This is the most common. It means the volume can be mounted as read-write by only one node at a time, perfect for most databases or single-instance applications. Read-only many, or ROX, allows many nodes to mount the volume simultaneously, but only in read-only mode, good for sharing configuration data or assets across multiple replicas. And read-write many, or RWX. This allows the volume to be mounted as read-write by many nodes at the same time. This requires a storage backend that supports shared access like NFS or GlusterFS. Very useful for things like shared file uploads or collaborative editing tools.
Choosing the right access mode sounds critical depending on the application's architecture.
It absolutely is. Using the wrong one can cause data corruption or prevent pods from starting. And finally, the reclaim policy. This is set on the PV itself, and it tells Kubernetes what to do with the underlying storage volume when the PVC that was bound to it is deleted. The 2 main options are retain and delete. Retain means even if you delete the PVC, the PV object and, crucially, the actual underlying storage volume, like the EBS disk, are kept. An admin would need to manually clean it up later. This is safer for critical data. It gives you a chance to recover it. Delete, on the other hand, means when you delete the PVC, Kubernetes will also delete the PV object and trigger the deletion of the underlying storage volume. Convenient for temporary stuff, but the data is gone for good. Storage classes often default to delete, so you need to be aware of that.
Wow, okay. Lots of control there. So retain for safety, delete for convenience, basically.
That's a good way to sum it up, yeah. Choosing the right reclaim policy is a pretty important operational decision.
This has been incredibly insightful. We've gone from the basics to some pretty deep components. For someone listening, maybe feeling a little overwhelmed, but seeing the power here, what's the main thing you want them to take away? What's the core concept to hold on to?
I think the absolute key takeaway is this. PVs and PVCs fundamentally decouple your application's need for persistent storage from the underlying storage infrastructure itself. Think about it. PVs are the cluster's pool of available storage resources. PVCs are your application's request for a piece of that storage with certain characteristics. This abstraction makes everything more flexible, more portable, and much easier to manage for both developers and administrators. Your app just asks for storage, the cluster figures out how to provide it. At the end of the day, it's what makes running stateful applications, the ones that need to remember things, truly viable and robust in a dynamic, often chaotic, containerized world like Kubernetes. It ensures your data is safe, accessible, and lasts longer than any individual pod.
That's a powerful summary. So for you listening, as you design or manage your Kubernetes applications, think about how this decoupling works. We've seen PVs and PVCs aren't just about saving files, they're about abstracting storage complexity, making it a declarative, cluster-wide resource, not just something tied to a single machine.
And this really leads to a fascinating final thought to consider. Given this flexibility, this abstraction layer that PVs and PVCs provide, how should understanding this change the way you think about your application's data requirements right from the start? Especially now, with cloud providers offering increasingly diverse and specialized storage options, ultra-fast disks, object storage, file shares. How does designing with PVs and PVCs in mind from day one better prepare your systems to be resilient, scalable, and ready to leverage whatever storage innovations come next?